We're here to talk about the nature of time, about what it is that makes us think that there's a particular direction to time or an arrow to time, about what it is that makes us think that moving into the past is somehow different to moving into the future. Now, on the one hand, this seems like a really obvious question to answer, right? Because when we see a scene playing out in our everyday lives, it seems immediately too obvious to us if we were to record that scene and play it backwards that we were doing so. We never see, for example, an egg that's cracked suddenly reforming into a perfect whole egg. And if we were to see something like that, it would seem incredibly unnatural to us. But there's a problem with this. And that problem is that Newton's laws of nature, which are supposedly the fundamental laws that govern how the individual particles and atoms interact with each other, Newton's laws are said to be time reverse invariant or time symmetric. So what does that mean? That means that if we were to zoom into that same everyday scene so that we could see each individual particle and how it's moving and how it's bouncing around, if we were to record that and play that in reverse, we would have literally no way of telling whether we were watching that film being played forwards in time or backwards in time. And the reason we would have no way of knowing is because Newton's laws of nature run exactly the same way forwards and backwards in time. So we have a contradiction here, right? On the one hand, we have a clear asymmetry and directionality to our large-scale observations of the world. However, when we zoom right in so we can see the individual particles and atoms, we've lost that asymmetry, we've lost that directionality. So if there really is a direction to time, if the future really is different to the past, then the reason for why this must be cannot be found in Newton's laws of nature alone. It must be coming from some other source. Entropy, signified by the letter S, as we move forward in time, always either stays the same or gets larger. So we never ever see a fall in entropy as we move forward in time. So let's imagine we have a horizontal box and we divide this box into 8 compartments and we have 16 marbles. So to start with, all the marbles are in one particular compartment. What we're going to do is we're going to perform an experiment with this, right? We're going to pick a marble at random and we're going to take it out of the box. And then we're going to put it back in the box, but we're going to do it in a random compartment. And we're going to repeat this process over and over and over and over and over again. By the time we've repeated this experiment a billion, a trillion times, even though it's very possible that we could, by chance, end up in this original position, we're much more likely to find a really even spread of particles around. The particles are almost randomly, chaotically distributed throughout each of the compartments equally. The only reason that this is the case comes down to what's called the occupation numbers. It's the number of ways that we can arrange the particles for each different scenario, right? So in this top scenario, there's only one way of arranging them so all the marbles are in compartment number 5. So the occupation number for that is 1. But if I am looking at this scenario where we have 2 marbles in each box, then the number of ways of arranging those are 817 billion. Right? And this is why it's just so unlikely that if we did this experiment a billion times, we'd end up back here. Because there are just so many more ways of arranging the marbles so that they end up in this configuration than to arrange them so that they're all in compartment number 5. So this example highlights what we mean by entropy. And entropy is a really important concept in thermodynamics. And what it means is, how many ways are there of arranging all the particles in the system so that they give rise to these macroscopic features which I'm observing? this initially highly ordered state has a very, very low entropy. There's only one way of arranging all the particles so that they're in this compartment, whereas there are 817 billion ways of arranging them so that there's 2 in each compartment. So what does this tell us? Well, this tells us that in nature, whenever we start with a highly ordered state, and we see these all around us, right? We have people, we have plants, we have planets, we have stars. Whenever we have such an ordered state where all the atoms and all the particles have to be arranged just so for that state to exist, then that is something that's fundamentally unstable. And it's fundamentally unstable simply because as the particles begin to jiggle around and as they rearrange themselves and as they move, which they must because everything is always moving, then the number of ways in which they can arrange themselves to be more evenly distributed are so much more numerous than the number of ways in which they can arrange themselves to be in that particular ordered state. And this tallies with our experience of time passing. This is why we never see a broken egg reform. Even if we started with all the air in this room up in one box in the top corner and then released it, it would fill the room and it would never fly up back into the top corner. And that's not because that's impossible by the laws of nature, it's just because it's so vastly improbable. Now, we started off by saying, right, well, we need to define an arrow of time, or what makes us think that there's an arrow or direction to time. And our common sense notion is of time as something that sort of chugs along independently of the rest of the universe, and something that sits apart but is always moving on constantly. And now we haven't found that here, but what we have found is something that is consistent with our experience of time passing. Because all those examples I gave you of systems changing forward in time, they're not really changing forward in time. They're moving from a state of low entropy to a state of high entropy. And that is what we pin our arrow of time to. We introduce time ourselves, and we say our experience of time passing is analogous to being on this curve from going a low entropy state to a high entropy state. We've talked about individual systems like the air in this room, or like a person, or like a planet, but really it's the universe as a whole that can be modeled as one of these closed thermodynamic systems. And it's that which gives a direction or an arrow of time to the entire universe. And now we have this very unusual picture that time is no longer something that's independent, that chugs along, but instead, time is just a description or a function of the arrangement of particles in the universe, right? Because the universe is one of these closed systems, and the universe itself is moving from a state of low entropy to a state of high entropy. We found a definition of time which is not independent and is not something sort of uncanny or otherworldly, but is really just a statement of the arrangement of particles in the universe, of how the universe is set up. Time is now something physical. It's something which is linked to the order and the chaos of the universe. And what we found is that the direction of time is simply this direction of increasing entropy. It's saying that you can start with all the order you want, you're always going to end up in this highly chaotic, disordered state. And it is that which makes us think there's an arrow of time. It's that which makes us think there's a direction of time. And it's that which makes us think that moving into the future really is different to moving into the past.
It's not a causal law in the sense that entropy is made to go up. It just happens that if you start off with something that's very ordered and allow this kind of process to take place, extremely high probability ends up in a disordered state. But there's a problem there, because I've used the word, it's just, there's a high probability involved in that. So that means that there's some small probability that that won't happen. So this was the insight that Poincare and Zermelo actually developed in the 19th century as a sort of a challenge to Boltzmann's view. So Boltzmann had thought that he'd derived or shown how you get a law of entropy increase, how entropy always increases to its maximum value. But Poincare and Zermelo said, well, hang about, this can't be the case. if you wait long enough, the low entropy states that you start off have to recur. And if you start off with a little bottle full of gas, and you open the bottle, and the gas comes out and spreads across the room, well, if you wait long enough, all of it is actually, you're going to eventually see it all go back into the bottle. And you might think, well, maybe that's actually something to do with some specific details of the dynamics. Maybe if you had a different dynamics, that wouldn't happen. But what Poincare and Zermelo proved was that actually, under a very general condition, that is inevitably going to happen. If you wait long enough, all of the gas is going to gather back in the corner room. And that means you can't have a law that entropy always increases, because those low entropy states are going to come back. And Boltzmann solves this by means of this bold cosmological hypothesis. If you imagine you've just got an infinite amount of time, if time just doesn't have any limit in either direction, and you just sit around and wait, most of the time the universe is going to be in a high entropy state. But every now and then, you're going to get a fluctuation out of equilibrium. It's going to go away from equilibrium, it's going to move into a low entropy state, but once it's moved out into equilibrium, it's going to go down into some value, and then it's going to head back to equilibrium again. And Boltzmann makes a remarkable suggestion at this point. If you look at the physical states as we're moving from the bottom of the valley to the top of the valley on our side of this curve, well, it's the same kind of physical states on the other side of the valley. But now those physical states are going to have memories still of the bottom of the valley. Everything is going to be working in the opposite direction. So they're going to see the direction of time in the opposite direction to the way we're seeing it. So once again, we come back to this idea, there is no flow of time, there is no fundamental direction of time in the physics. It's just that there's sequences of physical states, and what we perceive to be the direction of time is just where we are sitting. If we're sitting on one side of the valley, then we'll see the sequence of states going in the other direction. But there's no actual direction to time itself. It's just where we're sitting in the valley. Okay, well that sounds a bit crazy, but at least it makes sense, at least it explains things. But the problem with this point of view is that larger fluctuations, deeper valleys, are rarer than small fluctuations, shallow valleys. If you're flipping a coin and you're looking for sequences of heads, a long sequence of heads is a low entropy fluctuation. 2 heads in a row will happen fairly frequently. 10 heads in a row gets very rare, and 1,000 heads in a row you have to wait a long time for. The suggestion Boltzmann's making is that our universe and its early low entropy state is one enormous fluctuation out of equilibrium, is the kind of fluctuation that's going to be very, very rare. There's the evidence we have now for a low entropy past, whether it's archaeological evidence, it's films, it's books, it's carvings. All of these are records about a low entropy past that exists today. Now we can just suppose that they're true, but we could also say, well, hang on, what's the most likely explanation for all of these records to come about? All we need is to have a valley that's just low enough to fit in the world as we see it today. And that is a world, a valley, in which history doesn't actually go back very far before we have the bottom of the valley. That's a fluctuation that we've got equilibrium, and then in the middle, at the bottom of the valley, what we have is a set of records existing that do not actually represent what really happened. More likely than 10,000 years of human history that there was 1 million years of geological record was that there was actually only 100 years. But actually 100 years ago is still not the most likely, because 10 years ago would still account for all of our existing records. In fact, 10 years ago is actually still less likely than 10 minutes ago. That's less likely than 10 seconds ago. The most likely explanation for all of our experiences is all of this just came into existence a few seconds ago. But it's not just on time as well, it's also about space, because we point our telescopes out and we look out into the rest of the universe, and we think we see lots of structure out there. But actually, again, the most likely explanation is not that there's actually an entire universe that came into existence, The most likely explanation is that there was actually a very small area of space that comes into existence, looking as if there is an entire universe. Given that we're sitting here with our memories in this room, what's the most likely explanation of it from this point of view is that this room just came into existence about 10 seconds ago, and that's it. In fact, even worse. We end up with a situation where more likely even that this room and all of us, all of the books and so forth, in this room came into existence is that actually maybe it's just me. Maybe just I came into existence. And that actually everything that I'm seeing isn't real. It's actually just a bunch of photons that have come into existence, hitting the sensory inputs to my head, making me think that there's a world and other people out there. And that's more likely on this picture than that there really is a world out there. The most likely explanation for all of my memories and experiences is that I'm actually a spontaneously formed brain sitting in a bunch of thermal fluctuations that just happened to have all of the nervous and sensory inputs to that brain being stimulated in a way that makes it look like that there is a world out there that I am experiencing. It's a smaller valley to actually create just those sensory stimulations than it is to actually create a world that is responsible for those stimulations. But that means we've got into a very bizarre situation. We've now got to ourselves that if Boltzmann's picture is correct, then we're almost led to a point where we've argued scientifically that we should believe that the external world doesn't exist, that we should believe that time doesn't exist. We should believe, in fact, that other people don't exist. We've led ourselves into a scientific argument for a position called solipsism, that there is just you and your experiences. But it's even worse though, because why were you led to believe this? You were led to believe it because that was the picture that science gave you, that was the picture that physics gave you, because we went out and we did experiments and we discovered the laws of physics and we took our current best laws of physics and we worked out according to our current best laws of physics what the most likely explanation was for our experiences. Well, why do we believe in those current best laws of physics? Because we did experiments, or other scientists did experiments in the past and left records for us. But now, according to that picture, we no longer believe in those records. So the scientists never actually performed them. So why did we believe in those laws of physics in the first place?
I think the question of the limits of science is a super interesting one. When we think about time, it's one of those points where science and metaphysics start to really intertwine. And it's sometimes not so easy to tell when we move from one into the other. In physics, we see progression sometimes in how we describe the world. So you have Newtonian mechanics supplanted by relativistic mechanics. Quantum mechanics in the very small regime is very different from Newtonian mechanics. It reduces the Newtonian mechanics in the limit of large systems. So Newton's laws are still valid, but what we learned is they're only valid in certain limits. And the fundamental underlying mechanisms have changed. Mechanisms are super important. I think science effectively is studying mechanisms, but mechanisms aren't the whole story of why something happens or what its meaning is. So I'll give you a very simple example. You come into my home and there's water boiling on the stove. And you say, why is the kettle boiling? And I say, well, there's a thermal heat source that transfers energy across the container wall into the fluid, and that increases the mean square velocity of the water molecules, which is directly proportional to temperature. When that temperature reaches 100 degrees Celsius, there is a phase transition from a condensed phase to expanded phase, and that's why it's boiling. That's a mechanistic description of why the water is boiling. But you come into my home and you say to me, why is the water boiling? And I say, I fancy a cup of tea. Would you like one? And those are two very different descriptions of exactly the same event. And they're not opposed to each other, they're complementary descriptions. So science, it describes the laws of nature, it describes what they do, it describes when two things hit each other, how they're going to bounce away from one another, etc., etc. But it doesn't tell us where those equations come from. It doesn't tell us who breathed fire into the equations. There are probably three different ways of thinking of where the laws of nature come from. One would be to say, well, our current laws of nature were caused by another set of laws of nature that caused this one. And then the question was, what caused that set of laws of nature? Well, there was another cause, there was another cause, and you get an infinite set of causes. Now, that's possible, but science doesn't deal in infinite causes. That's a metaphysical approach. Another option would be to say, well, our current laws of nature popped into existence out of nothingness. And by that, I don't mean some kind of quantum vacuum, but true nothingness, ontological nothingness. No laws of math, no laws of logic, nothing, just boom, there they are. Those are two options, so an infinite regress or popping into being from nothing. And the third option would be that there exists some kind of being outside of space and time who may be a first cause, who is the origin of the laws of nature. And that would be the typical theological approach. And through history, you see theologians wrestling with this question, and this is one of the answers that they came up with, that this is describing God, who is outside of time, outside of space, and therefore can be an uncaused cause. All three of those different options are strange. All three are weird. All three are non-scientific. And to first order, you've got to pick one of those three if you want to ask the question, why is there something rather than nothing? And so I use this example just to show you that we all have to make this choice. And whether you want to have a God or not doesn't change the fact that you've got to make a non-scientific and strange assumption about the world. So I think a lot of people think that scientists would be typically non-religious, but I have a lot of colleagues who are deeply religious and also extremely good at science. It's obvious to us that there are many aspects of our lives that science simply doesn't describe, doesn't explain, like where does the laws of nature come from, or where do I get the value for a human being, or what does it mean to live a good life? Those are non-scientific questions. So you'll find in practice that there are often more overtly religious people in the sciences than there are, say, in the humanities at a university or in the social sciences. It's because I think the sciences naturally have a kind of religious sense to them. So if you're a religious person like myself, what happens is when you discover something really beautiful, it makes you think, wow, there's something bigger beyond this world. It's pointing towards something outside of the world. It's a kind of sign of transcendence. Just the same way when you stand on top of a mountain peak and you see an incredibly beautiful scene, and you think, wow, there's something more to it than just what I'm seeing. And science has exactly the same feeling to it. I think one of the things that happens when you see something about science is we feel our own finitude. We feel something small. But there's nothing new to that feeling. So throughout history, people looked at the stars and sensed that there was something small about them. There's a very famous quote in the Psalms where the psalmist says, when I look at the heavens and I see the stars, what is man that you are mindful of him? And I think all that our microscopes and our telescopes do is they enhance that ancient sense of wonder and awe. And so what Einstein is talking about is an enhancement of that sense of wonder and awe by discovering a law of nature. You feel very small. You feel like you're looking at something which is much bigger than yourself. And it's absolutely amazing.